So today we're, now that we've talked about priority queues, we are going to talk about another data structure. And this, in some sense, one can think of from many ways as the ultimate data structure in terms of operations that are supported. So what we would like to do, this is often referred to as the dictionary ADT, or it's also called a dictionary data structure. This is not the same as the dictionary in Python, which is basically a hash table. So this is a data structure which supports all the following operations: insert, delete, find, which is what a list could do. But then you can also do find max, find min. You can get what's called the predecessor. So the predecessor is the largest key less than a value, or the successor, which is the smallest key more than a value. So what we would like to do is to support all these operations. So there are 7 operations that I've listed here. Remember, the list does these. That's what the list does. The heap does insert, find max, and of course extract max. And the dictionary data structure does all these operations. And the data structure that does all these operations, which many of you may already know, is the binary search tree. Binary search tree, also called a BST. And one way to think about what a binary search tree is it's essentially in a linked list. So if you think about a linked list, whether you have singly or doubly, whatever have you, you have sort of basically a next. You may have a previous as well, but essentially the linked list sort of has a linear storage structure. In a binary search tree, every node is actually going to have 2 pointers going what are typically called left and right. So a node in a binary search tree, so I'm just going to give you the definition. So you'll have some object type data, which could be anything. It could be an object. It's convenient to think of there being a key which is separate from the data. This is the key is what you are using to search. And then it has 2 pointers called left and right. So this is the left child and the right child. So these are called the children. And then there is a third pointer, which in some senses is optional, is a parent pointer. This is optional. You don't necessarily need it, but it does make a lot of things easier. And this becomes the class or the basic node that one has in a binary search tree. Just like in a linked list, you have a node that has 1 pointer that points to next. A doubly linked list, you may have a pointer that points back, but fundamentally the structure is linear. Okay, so this is the class node. And the way that we'll sort of draw out the binary search tree is we think of, I'm going to use circles because that is sort of conventional. There's a circle at the top, which is often called the root. So that's sort of at the top of the tree. And so just like in a linked list, one had a head, so you have this class node. So the class binary search tree, and actually one can even just think of any tree is basically of this form, that there is a pointer to something called the root. Right? So the binary search tree class has a root, and then there are lots of nodes. And I will share my binary search tree code with you, which will have a lot of these details. And so whatever I'll talk about today, I'm going to do through pseudocode. So we have a root, and one has 2 pointers left and right to further nodes. And so let me just draw out a binary search tree for you. But sorry, just a tree. This is not even a binary search tree, just a tree of nodes. I'm not drawing out the parent pointers simply because then it becomes really messy. But you could imagine, so there's a lot of terminology about trees that I would like to define right now, which is important to talk through the various procedures that we will have to implement the operations. So the top of the tree, this is called the root. These nodes here, this is called a leaf. Excuse me. So what is a leaf? Node whose both children are null. That's what a leaf is. Sorry, this arrow might be confusing. This arrow is not a pointer, so just indicating that that's what leaves are. So in this case, there are 5 leaves. 1, 2, 3, 4, 5. The other nodes, these are called internal nodes. Internal nodes. Now, internal nodes have 2 types. Okay, so it can either have one non-null child, like so. So this is an internal node with one non-null child, and this is an internal node with 2 non-null children. So essentially any child that I have not drawn, this you should think of as null. This is null. So for this node, the left pointer is null. For this node, the right pointer is null. So for example, if x was referencing that node, then x dot right is null. Okay? So you have, yes? You don't have to have both children. Like you can just have a left child, and you can just have it have left, 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 and no right children. It's a good question. So any of the children can be null. Any child can be null, and we'll see examples of that. So this is a tree. A binary search tree is a special kind of tree. What I'm defining right now is a tree because I have not said anything about the values of the key in these nodes, and a binary search tree has a specific property on the keys. Okay. I just like to mute everyone. Yeah, okay. Okay, so good. So we have the terminology, the root, a leaf, internal node, and there's furthermore one more thing that I want to talk about. So let's say this is W. You could look at everything below W, and this is referred to as the subtree rooted at W. So W is a pointer to this node. The subtree rooted at W is basically this sort of portion of the tree, which is W, its children, its children's children, so on and so forth. Just like in a linked list, you could imagine that you have some node in the middle and you have everything after that as like a sub-linked list. This would be called the subtree. Okay. Now there are two more terms that I would like to introduce. So you have root, internal nodes, leaves, subtrees. Then you have a notion of an ancestor. So what is an ancestor? So the definition is recursive. X is an ancestor of Y if the base case is that X is the parent of Y. So if X is the parent of Y, it's an ancestor. Just think of it as normal genealogy, right? Your parent is your ancestor. And just to be clear, we can say X is an ancestor of X. So actually you can make this the base case. X is the ancestor of itself, and then the induction or the recursion is that X is an ancestor of Y if X is an ancestor of the parent of Y. Right? So in some sense the definition is recursive because it says X is an ancestor of Y if X is the parent of Y, or X is an ancestor of the parent of Y. So what this means is, let's say this is Y, this is an ancestor, this is also an ancestor, this is an ancestor, and the root is an ancestor. So all nodes in this sort of chain that go all the way to the root are ancestors. Sure. So it relates to the tree, you mean. So, okay, so let's look at what the ancestors of Y are. So we said X is an ancestor of Y if X is the parent of Y. So clearly that's an ancestor right there. So I'm just going to sort of shade the ancestor. Okay, that's an ancestor. But we also said X is an ancestor of Y if X is an ancestor of the parent of Y. And we know that the parent of a node is an ancestor. So so the parent of this node, so I'm going to refer to this, let me just refer to this as X1. So X2 is an ancestor of X1, right? Because X2 is a parent of X1. But X1 is an ancestor of Y, and X2 is an ancestor of X1, so X2 is also an ancestor of Y. The parent of an ancestor is also an ancestor, and that way X3 is an ancestor of X2, and therefore X3 is also an ancestor of X1, and it's also an ancestor of Y, and so on and so forth. Right? So all these nodes from Y all the way going up to the root, all of these are ancestors. So another way to look at this is that the ancestors form a path from X, I should say from Y, I'm sorry, because we're looking at Y, from Y to the root. And what is so it's Y, the parent of Y, the parent of the parent, so on and so forth. right? So you can go from Y, go to its parent, go to the parent, so on and so forth. Just as in a linked list, you can start from a node, you go next, 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 the next of that, and this gives you a path. Here, there's actually a path going up. This is assuming you have parent pointers, but this is sort of, in other ways, is sort of is follow the arrows backwards, right? Because over here in this picture, we're following the arrows backwards, and that gives us all the ancestors. So we have root, which is the top of the tree. We have internal nodes of two kinds, those that have two non-null children, those that have one non-null child. We have leaves. Then we have ancestors. And finally, we have descendants. Descendants. And so descendant is the opposite of an ancestor. So we'll say X is a descendant of Y if Y is an ancestor of X. Right? So it's just the opposite. So what this means is if you start at any node, let's say you start at W, anything below it is a descendant. So if you follow the arrows, you get a descendant. So the descendants don't form a chain. They don't form a path because they could spread out. So all of these nodes over here in this box, all the nodes in the box are descendants of W. Indeed, the subtree rooted at W is formed by all the descendants of W. So this is the same as all the descendants of W in the, structured as a tree. Okay, put together as a tree. Okay, so I threw out lots of definitions at you, lots of terminology. So let's pause and ask me questions, and I'm happy to answer any questions that you have about this. I'm just going to walk through each of these terms one by one. It's very important that you understand all of these terms because we will be referencing them many times during today's lecture. There is it doesn't store two objects. It stores only one object. It stores data and it has a key. It has two pointers. Sure, you can make it. That would be if it had 3 pointers. If it had 3 children pointers. Remember, the parent pointer is special. So if it had 3 children pointers, it would be called a ternary tree. You can, and there are trees of that form that are called B trees, where actually you have an array of pointers. But in some sense, a lot of that will only add complexity, which isn't necessary. It's the typical binary search tree would typical search tree would just have 2 nodes, left and right, which is usually enough for most purposes. But you can have more children. But it's, for a binary search tree, that's the word binary, and the binary refers to 2, left and right. Yeah. Yes. You can. I see. Actually, you're right that they're both the same. You can also say that X is a parent of the an ancestor of Y. That also works. The definition is the same. The way you implement it would be different, but this is not an implementation. This is a definition. But you're right. You could also say it's the parent of an ancestor. Yep, definitely. Mm-hmm. Correct. Yes, so don't think of this as a procedure. Like, think of this as a definition. What you're saying is like, how am I going to find this? Like, what is the while loop or condition I'm going to write? But let's not go there yet. I'm just saying that this is a definition, and make sure the definition makes sense. Then you're right that yes, you keep going until you hit the root. And the root is a node whose parent pointer is null. Right? So essentially that's the way that your procedure will terminate. So again, just to remind you, the root, that's like the first node of the tree. It's the top of the tree. Actually, you should think of the tree as being like, it's upside down, right? The leaves are at the bottom and the root is at the top. But that's the way we draw this. So the root is at the top of the tree. The leaves are at the bottom. The leaves have both children being null. Those are the leaves. Internal nodes have either two children or one child, two non-null children or one non-null child. So those are internal nodes. The subtree rooted at W. So if you pick a node, the subtree rooted is essentially all of its descendants together in their tree structure. All the descendants as a tree structure. This is a subtree. And then we have the notion of ancestors and descendants. So to get to the ancestors of a node, you just go to its parent, its parent's parent, its parent's parent's parent, so on and so forth. Just go up the chain of parents, and you will end up all the way at the root. This forms a path. This forms a unique path. To get to descendants, you start at a node, you go to its child, any one of its children, so on and so forth, and that gives you all the descendants. So by going down the arrows, down the tree, you get to descendants. By going up the tree, you get the ancestors. Okay, any questions? Exactly. It's easy to get the ancestors. The other thing also is that it's easy to determine if a node is the root, because the root is the unique node whose parent pointer is null. Good question. That may actually even be one of the questions that I will give to you. I have a list of questions on trees, and you will see how to do that when I tell you how to find a node. In general, yeah, so we'll get there. We're going to get there. In general, if you just have a tree and I just gave you a pointer and I say find all of its ancestors without parents, you would have to actually start from the root and get down to that node. Right? That's the way. So you'd have to go in the opposite direction, right? Instead, you have to start from its oldest ancestor, which is its root, and then try to follow the path down to get to the node. It's a good question, but store what? Well, I mean, if you wanted to output it, yes, but right now we're not talking about outputting the ancestors, right? I'm giving you these definitions because we are going to use these definitions in subsequent code and description, because now we're coming to the stage in the course where the descriptions of the algorithms are going to be much higher level. Like I might say, find the ancestor, and then when coded up, then you need to sort of follow the parent pointers. The BST class, the tree just has a pointer to the root. Right. Just like a linked list is just a pointer to the head. Mm-hmm. Yes, exactly. So I'm going to get to that. In a BST, the keys are organized in a particular way. Right now, what I described to you over here is just a normal tree. This is a binary tree. Now I have to tell you what a binary search tree is, and the search is going to enforce a condition on the keys. Just like in a heap we had this condition on the keys, the binary search the search is going to enforce that condition. So let me actually talk about that right now. So this is called the BST property. So as I said, so far what I told you was a binary tree. Now I'm going to tell you what the search is all about. So for all nodes X, this is the condition. So here's X. For all descendants Y. So Y is a descendant of X. We'll say if Y is a descendant of X arrow left. So this is how I usually draw my trees. That means that if Y was in the left part, then the key of Y is less than equal to the key of X. Okay, so this is the condition that we will enforce. I will say if Y is a descendant of X arrow right, then Y dot key is going to be greater than X dot key. If the equal to is bothering you, you can actually have the equal to be either here or here. You don't want to keep it on both, because then when you're searching for things that are equal, it becomes confusing. So typically the equal would be on this side or on this side, but not both. And I have kept it to the left. For a lot of the things that we're discussing, we can assume all the keys are distinct just for convenience. But in general, when you code it up, you have to be cognizant of this and careful about that. So what this is saying is that all the keys here, all the keys are going to be less than the key of X, and all the keys here are going to be, strictly greater than the key of X. This is the binary search tree property. And just like in heaps where we have this condition, in a binary search tree, this is the condition that we have. We have this condition on the keys. Any binary tree storing nodes which has this property on the keys is called a binary search tree. This is what defines a binary search tree. And that's why you need to know what descendant is, because one uses that definition to define a binary search tree. Yes. Yes, because by our definition, X is an ancestor of itself, and therefore it's a descendant of itself. No, you should think of the key as something. Key you can think of as part of the data. If the data is bothering you, can remove it and imagine you're just storing integers. But one way to think of it is in the Twain assignment. You were storing words and frequencies, so maybe their word would have been your key, and your data is the frequency. Questions? Okay. Now that we have a binary search tree, let's talk about how to implement the various operations. That's find, insert, delete. And you'll see that find min, find max, predecessor, and successor are going to be quite easy. given those properties. One of the sort of the main ideas is, in a binary search tree, it's easiest to write recursive code. Recursive code is the most simplest way to perform lots of operations. And you're going to see this right now when I just do find. So my find function, because I'm doing recursion, I'm going to have a pointer to start. So this is going to be some node in my tree. So here's my tree here, and this is some node. And I'm trying to find it in the subtree. So this is going to find, and I'm going to search for a key called val. Right? So this is going to find a single node with key equal to val in the subtree rooted at start. That's what this function is going to do. It's not going to search through the whole tree. It's only going to search through the descendants of start. And then we'll do this recursively, and then you'll see that all you have to do is call this function at the root. Okay? I'm going to write things sort of in English pseudocode. I will give you my C++ code that you can look at. So for the base case, we'll just say if start is null, then you just return null. If the key of start is val, then you simply return start, right? Because then you found the node. Now for the third question, the third part is if val is less than start arrow key, then we're going to return something here. So if val is less than start arrow key, then what? So let me give you a few options and you tell me which one is right. I'm just going to poll you on this. There's my code so far. The question is, I'm just going to move that sort of a little further up. Sorry. All right, there you go. The question, so what is the next, what's going to go over there? What is going to go in the return? So is it going to be return find start arrow left val? Is it going to be return start to the right of val? Or is it going to be return at the parent of val? And let me now start the poll. So is it start arrow left, start arrow right, or is it find to the parent? right? So seems there is a little bit of confusion. So the answer is this. So why is that? So remember that the binary search tree property, let's go back to the binary search tree property. We said everything whose key is smaller is in the left side, and every node whose key is larger is in the right side. Our aim is to find a node in the subtree rooted at start. So there's no need to go to the parent. We're actually looking below. Now, a val is less than start arrow key. If there's any node, so here there's the two children subtrees. If there's any node with val, it has to be in the left side. It cannot be in the right side. Right? So because val is less than start.key. And so this is going to return find start arrow left of val, and the else condition you return start arrow right of val. So these three statement 2 and the return statements in 3 give you sort of the three conditions. When start arrow key is the same as val, then you've already found it. If it's val is less than start arrow key, move to the left. And if val is more than start arrow key, move to the right. So hopefully you see it's sort of similar to binary search in that way, right? You make a comparison, you move either to the left or to the right. And in some sense, a binary search tree has been designed to achieve the fast search of binary search. Any questions about how find works? Yes? Exactly. It returns the, yes, this would return the highest node in the subtree rooted at start. So remember, this is the function, this is the recursive function. You have to come up with the dummy function, which is again not hard, right? You simply call find at the head, starting at the head. But you're absolutely right. You would return the highest. Just like when you're doing find in a linked list, you return the earliest, the first node that you see. If you're trying to find everything, then okay. So this is a good good question. So this is exactly why the equal to is only on one side. So if you wanted to find everything, then let's just say when you find this, you would, maybe print the value, but you would go to step 3, and again you would go to the left, right? Because with the less than equal to, you'll go to the left. So you'll keep going to the left. So it is convenient to you to do that. It is convenient to do that. Things become kind of problematic when you have lots of equal keys. We'll see that when we talk about self-balancing trees, it becomes really messy. So it's best to think about all the keys being unique. Eventually, your recursive, your dummy function or whatever, you have this one function that is non-recursive that just does find. It is going to call the recursive function with the root. Yes, this is trying to find a single node whose key is val. So if it's a duplicate, so if they're duplicates, then there could be multiple keys in here. This just returns like the highest one. Yeah. Any further questions? Yeah. So we'll get to that. Yeah, I mean, that we're going to have to talk about, which is what is the running time, and that's going to be a long, more complicated discussion. Yeah. Yes, so I mean, yeah, that's a good point. I mean, it's important to note that, you know, typically you try to set things up so that you don't have duplicates, because if you insert a duplicate, then you would sort of go and update a frequency or something like that. In general, I have set this up in a specific way, but you know, it's better to, like, you know, for now, and you may have the equals. When we talk about self-balancing trees, things get a little complicated. It's useful to think of keys as unique. All right, so we've done find, and so once we've done find, now it's natural to do the next step would be insert and then delete. And I want to stress that, you know, my code doesn't cover all the corner, my description here doesn't cover all the corner cases. My code does. I want you to understand the basic logic before we get into discussion of corner cases, which I may skip during the lecture, but you can look at my code to see those. And typically one of the common, maybe I should just write this out, a common corner case usually involves empty trees or something like deletion of the root. Right, so and typically things that create empty trees are going to operate on empty trees. These are common corner cases where you have to write some separate code that will prevent a seg fault, and I'm not going to write this out in the pseudocode. So let's now talk about insert. And again, as I said, we'll do recursive. So we'll insert with a pointer to some start node, and let's just say that I'm going to insert let me say I'm going to insert some object that needs to be inserted, and there's, let's just say toInsert has some key. This has some key value that we're inserting. So it's just convenient for me to think of this sort of entire thing as the object, because I don't want to carry all the separate arguments around. So you want to insert some object that is the key, and this is the key. So what this is going to do is insert the object to be inserted in the subtree rooted at start. Okay. Now the code tends to be a little large. There are multiple cases, and I don't want to write all the cases because, again, you'll see that they're quite analogous. So let me sort of write it out in English without being very careful about code structure, and I'll answer any questions that you have. I think once the logic is clear, you'll be able to write the code. It's not very hard. So let's just say that suppose the key was actually less than this key. Again, I put a dot here because I think of the object having the key, and I put an arrow here because start is a pointer. Okay, so this, think of this as the object having a key. Okay, so here's start. And now what we need to do is we need to insert it in the left side. Now if start arrow left is null. So there's nothing there. Then we go ahead and we insert. So this is going to be our base case here. And so we have 3 steps then. We make start arrow left is some new node. And then we'll make the new node dot data equal to whatever data we want to insert. Maybe I should. And then we make the parent of this be start. Right? So there are basically 3 lines of code. And this is the base case. Right, so if this was null, we'll go ahead and create a node over there. We'll put the data, the appropriate data in here, and then we'll just set the parent pointer to that. I haven't written the constructor of the new node, but you can assume that if you create a new node, then these pointers are just going to be null because this is a new node. So this is the base case. Otherwise, you just do an insert at the left. Now it's important to note that this entire block assumes this condition. And so when, if toInsert dot key was more than start arrow key, then switch all left to right in the above code. So you just switch all occurrences of left to right, and you'll get the exact same logic. So first, let's understand this again. So if you wanted to insert at the subtree rooted at start, you have, first you check. So essentially it boils down to 4 different situations. You first check, is the key of what you want to insert less than start arrow key, or is it more? So if it's less than equal to, then you have to insert on the left. Now this is sort of like the big case. This is the left case. Now within the left case there are 2 subcases. What is the first subcase? Is that this is null. So this is start, and that's null. So in this case we have found a place to insert. We go ahead and do the insertion. Otherwise we do the recursion. So in this case what we do is we simply move to start.left, start arrow left, and then do the same procedure. This gives you the 2 cases here. The 2 cases here would be, again, that's start. Right, so you see these 4 cases that I've drawn. In these 2 cases you want to insert in the left. In these 2 cases you want to insert in the right. And these are the 4 cases that need to be considered for insertion. So are there any questions about that? Exactly. So note that it might be the case over here that this has got other nodes on this side. So start might not be a leaf, but if the left child is null, then you just go ahead and insert. Remember that this left case may make recursive calls to the right case. It's not that left is just going to keep going left. Like, you have to write this entire code over here, and that whole thing is the final code. Right? So the actual insertion path will go left and right and right and left, so on and so forth. Yes? Yes, you have to check if start would be null and return. But, so good. So that's actually one of the corner cases that involves an empty tree. In this code, I've assumed that there's already something at start. But you're absolutely right. You would need, so what I have written here deliberately is not a very precise function. I've kind of written it in this pseudocode style. You're right that if start is null, then you have to think about, but you still have to do the insert. So where are you going to insert now? Mm-hmm. It will be inserted, it will become a leaf. Yes. There is no sorting that is happening, right? You start with a binary search tree and you insert into the binary search tree. Right? So you start with a binary search tree. You start with a tree that has this property. Now you want to insert a node into this, maintaining that property. Okay. No, wait, so you cannot have that, right? So if the root was 100, then the right one has to be more than 100. Okay. Mm-hmm. Insert. You want to insert 40. Good. So you're going to start here. You're going to go to the left. Then you're going to go there, and then you're going to go to the right. And then you insert 40 here. It will always go to a leaf. Well, it doesn't. This doesn't have to be a leaf, because maybe this actually had 10. So when you didn't insert 40 yet. So you would go down here. Then you would look to the right. You would say, okay, the right is null, and then you insert 40. Whatever node you insert will become a leaf, but the parent may not have been a leaf in the previous step. Yes, then it would have gone to the left of that, exactly. It's almost like you're following the search procedure. You're following the search procedure until you get to a leaf, or you get to the end, not a leaf. I'm sorry. You go to the end, which is a null node, and then you just create the new node there. You mean why I didn't put the thing into a node first and then? No, not necessarily. I could have done that as well. I could have, maybe that actually in hindsight that would have been the better thing to do, just to insert a node. I'm sorry. You're right. You assume that when you create a node, all the child pointers are null. Yeah, so that's like a constructor for a new node, right? So which is just like a constructor for a node in a linked list. Any other questions? over here, you would basically, at some point when you finally do the insert, at that point, you have the parent, right? Because you insert it somewhere. So whenever the insertion happens, you're either in this case or in this case, at which point the parent becomes the start, of that recursive call. Where would you insert 39? So let's walk down this, right? Right. So you would start at 100. You say 39 is smaller, so you go down here. 39 is larger, so you go down there. 39 is smaller, so you go down there, and then you insert 39 here. So I have put up a link to a visualization, and you can look at that visualization, play around with it, so that you understand the various cases. Again, I will try to I wanted to, I guess the thing is, I toyed with, do I want to show you the visualization during class, or do I want to cover the code? So I want to sort of cover the logic as much as possible. And I think with the logic and the code that I provide in the visualization, it'll definitely, it'll make sense. These pictures, of course, are very useful to draw out to see what's going on. Yeah? No, you can store whatever you want. The key has to basically be key has to be in a total order. The only thing is that you should think of the key needs to be something that can be compared. You can just store any kind of object you want as long as the key is what's called total order, meaning that you can essentially sort all the keys. As long as the keys can be compared in a consistent way, it doesn't matter what the actual type is. I'm just using int over here because it's convenient. Yes, the key, exactly. The key is the index. Any other questions? Okay. And actually, in hindsight, given one of the comments someone had said, it would have been I think the right thing for me to do is to not make this an object, but actually have made this a node. So I could have taken the object that I wanted to insert, put that into a node, and then use that. That is actually what I should have done. So my apologies. That would have made things a lot more clearer, but it's essentially the logic is identical. The logic is identical. Okay, so just maybe I should just say that. I could have made this a node, right? So I want to insert the node pointed to by this and then at that case, this would have simplified somewhat. I could have just said that start.left is to insert. And then I would say to inserts parent is start, right? So it would just be 2 lines. Okay, so the final function that we're going to talk about is delete. And delete is complicated. It's complicated, or it's more complicated. It's not too bad once you break it down, meaning that there are many cases. So I'm going to think of the function delete node. So I'm going to start with a pointer to a node that I want to delete. So this is a pointer to the node that needs to be deleted. How would you get this pointer? Well, you could do a find to find the node that you want to delete. Right? So you could probably find something that you want to delete, you get the pointer from there, and then you call this function with the pointer. We'll see that it's going to be much more convenient to do this with the pointer. And I'll say that if toDelete is the root, it's a special case. So there's some additional work that needs to be done. I'm going to leave that as an exercise for you to figure out what are the additional things you need to do when it's the root. I will give you the code, and you'll see that when it's the root, you'll have to do a little bit more. Okay, and this is also given in the code that I will provide to you. Okay, so I'm going to break up delete into 3 cases. So case 1 is the easiest, and at this point, it's sort of complicated enough that I'm not going to write out the code, but I'm going to explain the logic, and you should be able to convert this to code. So the easiest case is when the node that you want to delete is a leaf. Right? So that's when, let's say this is toDelete. This is the node that you want to delete. Delete. And this is just a leaf, so it doesn't have any child pointers here. So in this case, it's actually quite easy. All you do is you can just set that to null, and you'd be done. And then you can, of course, return the pointer. You can do whatever you want with toDelete, free it, not free it, and whatever is appropriate. The important thing is how do you change the tree. So what you say is, well, toDelete is either the left or right child of the parent. I'll refer to the parent as X. So you simply set the appropriate child pointer of X to null. And then the deletion is done. Right? So you've effectively removed it from the tree. So this is the simplest case. Note that this is going to require like some kind of if-else code that you need to write. Right? You need to figure out, is it the left child or the right child, and you need to set the appropriate child pointer to null. Case 2 is toDelete has exactly one non-null child. So here's the node you want to delete. This is toDelete. Its parent is X. And this has exactly one child, and so that child might be Y. Now there are actually 4 cases here, because it could look like X. Remember, toDelete is always the middle one. It could look like this, or it could look like that. Right? So there are 4 cases where there's exactly one non-null child, but the deletion actually happens to be quite easy in this case. And so there's X, and that is Y. Right? So toDelete is basically the middle node here. So in this case, you can splice. So splice means you can just remove that node, and you just make Y become a child to X. So you simply remove that node. Splice, so Y becomes child of X. And of course, you need to sort of set the child pointers of toDelete to be null to ensure to prevent memory leaks. And but I'm not going to write those conditions out here. So what happens here is, let me just explain one case and you can work out the other cases. So I'll explain maybe this case over here. So in this case, what we're going to do is we're going to say, let me just make sure I get this right. So we say X. Okay, so what was X? This is the parent, right? And what is Y? That was the left child. So we will set X arrow left to Y, and we will set Y's parent to X. So we're going to start from here and we're going to end up with that. Remember, Y was the left child of the node to be deleted. There was my mistake. But it ends up being the right child of X. This is really important. Even though Y was the left child of the node to be deleted, it becomes the right child of X. And that's because all the keys over here have to be more than the keys of X. And so the key of Y is more than the key of X. The key of Y is more than the key of X. And so this is the right way to do it. This same logic will happen here as well. Except in this case, in the second case, it would be Y is to delete arrow right, not left. And in these other cases, you'll have to sort of switch around what left and right are. So this is the second case where to delete has exactly one non-null child. Any questions about this? Is there any questions in the chat? Let me know. Four cases for one non-null child, right? Exactly. So there are lots of cases, because case one, where to delete is a leaf, actually has two cases, whether to delete is the left or right child, because that will change the exact pointer. So there are two cases here. There are four cases over here. First question, what is the running time in this case? What is the running time? To delete the leaf, if you have a pointer to the leaf. Just in this case. It's O of 1, right? Because all you have to do is switch a couple pointers. Well, I wouldn't say n is 1 here. The tree could be really large. But you're only deleting a leaf. You already have the pointer. And over here again, it's again O of 1. It's just a bunch of statements, right? It's all constant time, because all you need to do is just switch around a bunch of pointers. Okay. All right. So we did the simplest case, the medium case, and now we do the complicated case. Now we do the complicated case. So case 3. So case 3 is to delete has two non-null children. Okay, so here's what to delete looks like. And so there's some subtree here, and there's some subtree here. So it turns out that instead of actually trying to delete something, what is convenient is to replace the data and the key in toDelete with the data and key from another node, and delete the other node using cases 1 and 2. Okay, so this is kind of clever. What it's, instead of actually trying to delete that node, which could affect the tree structure, you try to find some other node that is easy to delete using cases 1 and 2, and you swap the data. Okay? So let's try to understand. Okay, so I'm just going to refer to this. Well, okay, so let's not. Suppose I want to replace the key over there. Okay? So I want to replace the key. Remember, this is just a pointer to a node, so I'm actually not going to delete that node. I'm not going to delete that node. I'm only going to replace the contents of that node with the contents of another node and just delete the other node. Okay, so what should I replace this with? What should I replace it with? This one? You can find the biggest value on the left, the largest key in the left, or you could also do the smallest key on the right. Right? They're both the same. So you find the smallest key in here. So either you find this node or you find this node. This is the smallest key in the right, and that can go here. So let's do this a little bit carefully. So I'm going to refer to this as X, and this is Y. So what is Y? So X is the right child. Y is the smallest, I'll say the smallest node, and you know what I mean, right? It's the node with the smallest key. It's the smallest node that is a descendant of X. Now let's kind of understand what this means. It means that you pick any other node Z. For all Z in this subtree, right? The key of Y is less than equal to the key of Z. That's just by definition because you pick the smallest node. But you also know that Y's key is bigger than any key here. So if you pick any W, you also know that for all W, the key, or I should say arrow key, that is less than equal to delete arrow key, which is less than equal to Y arrow key. Actually, this is a strict inequality. So all the keys here are less than the key there, And any key over here is greater than that key. Therefore, y arrow key, the key of y, is more than the key of w for any w in here. But the key of y is also less than all the keys in here. That's by choice, by construction, if you can find that key. And so if you swap y's data over there, then you'd be safe. And then you can delete y instead. Good question. Good question. What happens if y has children? How many children can y have? It can only have one child, or it has no children. So y is either a leaf or y has one child, but then you could just go to case 1 and case 2. Because then the node you're trying to delete is a leaf or it has exactly one non-null child. So y is the smallest node that is a descendant of to delete arrow right. How do you find y? How do you find y? Start from x and keep going left. And you keep going left until you hit null. So you know that y cannot have a left child. Therefore, y has at most one non-null child. So now let me write out the logic. So I'll say starting from to delete arrow right, keep going left until we hit null. Call that node y. Right, so that gives us y. Then we'll do a swap. So we'll swap the content, right, which is the key as well as the data of to delete with content of y. So we'll swap the content, and then we just call delete node on y, and y has, the key is that y has at most one non-null children, or child, I should say child, has at most one non-null child. So delete node of y, is, case 1 or case 2, which we already know how to do. Okay. Okay, so any questions about this? This is a fairly complex piece of code here, and that's why I didn't write it out, because it ends up being a fairly large number of lines. The important thing is you break it up into 3 cases: cases 1, 2, and 3. Case 1 is easy. It's when the node you want to delete is a leaf. Case 2 is when the node you want to delete has exactly one non-null child. You have to splice. So it's not that complicated. There are there are 4 cases, but in each case it's just manipulating, I think, two pointers. The really complicated case is when to delete has 2 non-null children. In this case, you actually have to do a data swap. So you go to the right and you keep going down until you hit the minimum node in this subtree rooted at x. You can also go to the left and keep going rightwards. Both of these approaches work. Both of these approaches work. And then when you hit y, you swap the content of toDelete and y. So you swap these two nodes. You swap the content of those nodes. And then you call toDelete on y. And this is going to be in case 1 or case 2 because y does not have a left child. And that is the logic of delete. Any questions? Yes? Mm-hmm. Right, so it's you don't swap with x, you swap with toDelete. Yeah, exactly. And it's not just the comparison with the child, but the comparison with all the descendants on the left and all the descendants on the right. That's important, right? So because when you move this here, it's not just the comparison of y's key with x's key, but y's key with z's key, where z is any node in that subtree. That's why you have this sort of for all condition of y and z, and you have a for all condition of w, where w is a node here. Hmm? I don't. There's usually no reason to pick one over the other. It's complicated to do both. You could also you could look at both and you can say, okay, maybe one of them is a leaf, so that's easier. Typically from efficiency standpoint, it wouldn't matter. But then if you did that, your code would get overly complicated. Mm-hmm. The only difference, the difference is you would have to then reassign the root. Like actually not in case 3. In case 3 you don't have to reassign the root. But often root will end up being cases 1 or 2, in which case you have to reassign the root. And that's a source of lots of bugs. Like trust me, when you start writing a tree code, often you'll get a seg fault. That's because there's something wrong with the root case. The root case doesn't really affect you in case 3, but it affects you in cases 1 and 2. Mm-hmm. So good. It's O of 1 only in cases 1 and 2. Over here, you're absolutely right that you have to traverse, but there's no reason why that's going to be log n. It's the depth of the tree, and you don't know what the depth of the tree is. The depth, it could be much more than log n. So that is actually going to be the topic of the next lecture, where I discuss what you're saying is if the tree was actually balanced, then it would be log n. But what if you did all kinds of deletions to make the tree imbalanced? Yeah, exactly. They aren't symmetric. So you could have trees with that, and then trying to fix that problem is a fairly complex process, which we'll be talking about in the next lecture. Yeah. Mm-hmm. So I don't know. So you have to maybe you have to use the names here. So which ones are you swapping? No, you don't swap x with toDelete. We swap y with toDelete. Yes, y is smaller than x, which is what it should be. Y should be smaller than x because everything here should be bigger than what is here. Yeah. You'll see that like this is a bit. So I'm pretty sure if you sit and write down the logic here, it'll be clear. Or if you draw an example and use the visualization, it'll be crystal clear. You see a few of them and then it'll be clear. Like now that you understand the three cases, go and try to draw out your own tree actually. Draw your own tree. I will put my code, make my code available, use my code, and it will be pretty clear. Excuse me. I'm sorry. What's the... Right, so this delete function takes a pointer to the node that needs to be deleted. You get this pointer through finding. And the reason, just to be clear, why am I defining delete node this way and not the way that you said, is precisely because I need to make a recursive call here. And because I need to make a recursive call with the pointer, it's convenient to have a function that takes as input the pointer. So if you didn't have parent pointers, then it kind of starts looking like a linked list where to delete a node, you also need to send a node to the parent. Right? So if your recursive function over here sent two arguments, which is the pointer to the node to be deleted and a pointer to the parent, then you can get all of these things to work. So it's just a matter of then the outer procedure where you're actually doing the deletion has to now keep track of all of these, has to send these pointers appropriately. My code has parent pointers, yeah. So it's three cases at the top level, but then each of the cases has subcases. And so case 2 has 4 subcases. Case 1 has 2 subcases. Yeah. In the worst case, you're right, it is O of n. Yeah. And but we'll be discussing this the next lecture, which is the runtime of these operations. Okay, so actually, I will, let me end here.